You are listening to DTFHN for May 16, 2026. I'm your open source to the bone host, Jack Haxman. We are your daily tech feed for Hacker News, a website where people argue about things they built at 3 a.m. Today's episode is a love letter to the stubborn, beautiful act of making things legible. Strap in, nerds. Thick-sized. 2 words buried in the architecture of this paper, and they reveal everything about where we actually are with AI memory. Δ-Mem proposes a bounded memory system for large language models, a way to remember things across conversations without the context window growing until your GPU catches fire. Here's the detail worth lingering on. Every memory system we've built for decades. Databases, caches, file systems. As a fixed capacity with an eviction policy, this has solved engineering. Your CPU's L1 cache figured this out in the 1980s. And yet, in 2026, a research paper proposing what if the AI's memory had a size limit is novel enough to publish on Archive. Run this forward. Right now, every conversation you have with an AI starts from scratch. Your coding agent doesn't remember that you hate semicolons. Your writing assistant doesn't remember your style. The comments on this paper nail it. One person points out that millions of users ask nearly identical questions, and every single time the system burns compute reconstructing the same context from nothing. It's like if every time you walked into your office, someone had wiped your whiteboard, shredded your notes, and you had to rederive your project from first principles. The comedy here is architectural. We built language models so powerful they can reason about quantum mechanics, then gave them the long-term memory of a goldfish and called it a feature. The context window isn't memory, it's short-term attention. The difference matters the same way RAM matters differently from a hard drive. And we spent 2 years pretending one could substitute for the other. Another commenter asks the question that actually matters. Has anyone tested these memory techniques in real, sustained use? Not benchmarks, not contrived recall tasks. Actual humans, over weeks, building trust with a system that remembers. The answer, mostly, is no. We're still in the proposing mechanisms phase. The validation gap between works in a paper and works in my workflow remains enormous. What makes Δ-Mem worth watching isn't necessarily the specific technique. It's the fixed size constraint. Bounded memory forces hard choices about what to keep and what to forget. That's not a limitation. That's intelligence. Your brain does this constantly. The interesting research isn't how do we remember everything. It's how do we forget correctly. The paper is on Archive. The code presumably will follow. And when memory systems like this actually ship in open tools, when your local model remembers you across sessions without phoning home to a server, that's when the architecture of AI stops being a subscription and starts being a relationship. Now, memory is one kind of elegance, but there's another kind that lives in how we talk to hardware. What does it take to make parallel hardware actually accessible to working programmers? Not accessible in the marketing sense, where you still need a PhD in CUDA to get anything done. Accessible in the sense that you write what you mean, and the compiler figures out how to scatter it across 10,000 cores. In 1957, John Backus and his team at IBM shipped Fortran, and the argument against it was identical to what you hear today about high-level GPU languages. It'll never be as fast as handwritten assembly. Real programmers don't need abstraction. Fortran won because the compiler got good enough, and suddenly, a generation of scientists could think about physics instead of register allocation. Futhark is making that same bet for massively parallel hardware. It's a pure functional array language, statically typed, and it compiles to OpenQLE and CUDA. The key insight, and this is where the engineering craft deserves real admiration, is that purity and immutability aren't just academic aesthetics here. They're what make automatic parallelization tractable. When you guarantee no side effects, the compiler can restructure your computation freely. It can fuse operations, eliminate intermediate arrays, choose between sequential and parallel strategies per expression. The type system isn't ceremony. It's information the compiler needs to generate code that actually saturates modern GPUs. Look at what people have built with it. A falling sand game, ray tracers, a lattice Boltzmann fluid simulator, a full compiler, Terrayas, that parallelizes parsing itself. Someone implemented the Poseidon hash function for Filecoin's GPU pipeline. These aren't toy benchmarks. They're people reaching for Futhark because it was genuinely the right tool. And the community signals matter. Bug reports fixed within a day. A maintainer who responds at a speed that suggests this isn't a side project gathering dust. It's a living system with momentum. The entire language, compiler, and ecosystem are open, BSD licensed. You can read every optimization pass, every code generation strategy. When someone figures out a better way to fuse parallel reductions, that knowledge compounds for everyone. This is how programming languages should evolve. In the open, with the implementation as legible as the documentation. The question isn't whether we need higher-level abstractions for parallel hardware. We obviously do. The question is whether those abstractions will be proprietary runtimes controlled by chip vendors or open compilers that anyone can study, modify, and improve. Futhark chose correctly. 3 stories in, and we're still talking about things that belong to everyone. I love today's lineup. Next up, pause Project Gutenberg. In Italy right now, if you type Gutenberg.org into a browser, you get a page that says, Police Notice. This site is under judicial seizure. 75,000 public domain books. Seized by police. Books whose authors have been dead for a century. Digitized by volunteers offered for free. And somewhere a court decided this needed to be stopped. That's the backdrop against which Project Gutenberg just keeps quietly getting better. One of their programmers showed up in the comments to say they've been overhauling the site for months, with more coming. The new executive director popped in too. This isn't a museum piece. It's an active project with momentum, 55 years into its run. 55 years! Michael Hart started this in 1971. Before the web. Before personal computers were a thing normal people owned. The man typed the Declaration of Independence into a mainframe terminal and said, "What if we just gave people books?" That's the whole thesis. No business model, no engagement metrics, no subscription tier. Just books, digitized by thousands of volunteers who proofread them line by line, given away forever. And here's what the bootstrapism lens reveals. Every major ebook vendor could integrate Project Gutenberg as a free library inside their store. 75,000 titles. No licensing fees, instant catalog depth. Instead, as one commenter points out, they're actively hostile to it. Because free books that never expire don't generate recurring revenue. The latter gets pulled up not by technical limitation, but by commercial architecture. The device in your hand could access all of it frictionlessly. Someone chose to make that harder. Meanwhile, one commenter bought his father, a GED holder, not a literary scholar, a Kindle, and showed him Project Gutenberg, the old writings, the great literature, available to anyone with a connection and a screen. That's the promise of open access actually delivered. No gatekeeping by education level. No paywall calibrated to what the market will bear. 75,000 books, thousands of volunteers, 55 years of continuous operation, no venture capital, no IPO, no pivot to AI summarization, just the radical, persistent act of making knowledge free. The tools exist, the library is open, in most countries anyway. Now, from the elegant simplicity of a free library, let's talk about the opposite impulse. Story 4. We've made the world too complicated. Every system I've ever built started simple and got complicated. That's not a flaw in engineering. It's what happens when you solve real problems for real people. The question was never whether complexity would arrive. The question was always whether the complexity served the user or served the operator. A post making rounds today argues we made the world too complicated. The author wants to snap a laptop at the hinge, throw a phone into the ocean, walk away from all of it, and the comments split predictably. Half saying burnout, half saying Luddite. Both miss what's actually being described. Let's break this down to first principles. Complexity comes in two forms. There's essential complexity, the irreducible difficulty of coordinating 8 billion people, growing food, distributing medicine, communicating across languages and continents. That complexity exists, whether you have computers or not. Pretending otherwise is nostalgia for a past that killed most of its children before age 5. Then there's accidental complexity, the login screen that requires an app, that requires an account, that requires a credit card, the thermostat that needs firmware updates, the medical bill that takes a forensic accountant to decode. That complexity isn't solving your problem, it's solving someone else's problem. Usually the problem of how to keep you dependent on their platform. The author writes about living in a building with rooms they can never enter, governed by laws they can't control, surrounded by technology they'll never understand. That's a precise description of closed systems. Every one of those frustrations traces back to architecture, where the user has no agency, no visibility, no ability to modify what isn't working. One commenter cuts right to it. Be suspicious of complexity that gives no corresponding increase in dignity, beauty, autonomy, or peace. That's the filter. Apply it ruthlessly, and you find that most of the complexity crushing people isn't from technology, it's from enclosure. Proprietary systems, artificial gatekeeping, interfaces designed to extract rather than empower. The answer to a world made needlessly complicated is not fewer tools. It's tools you can actually open, inspect, modify, and share. The author's intuition is correct. Something is deeply wrong with how most people experience technology. But the diagnosis points toward better architecture, not abandonment, toward systems that are legible to the people who depend on them. The wind and the water and the birds aren't going anywhere. Neither is the technology. The variable is whether you get to hold the wrench. This one's fascinating and a little bittersweet for the hacker community. One commenter replaced the word CTF with university and said, "You've just described the total collapse of education." that substitution lands harder than it should. The article's argument is straightforward. Frontier AI models now solve enough CTF challenges to dominate scoreboards. Beginners who would have climbed that ladder, building real security instincts through struggle, now face a choice between genuine learning and prompt pasting their way to points. The feedback loop that made CTFs valuable as a training ground is corroding. Let me push back on this for a moment. You could argue that CTFs were always artificial. The challenges are synthetic. The vulnerabilities are planted. Real security work doesn't look like a 48-hour sprint through increasingly obscure puzzles. Maybe AI clearing the scoreboard just exposes that CTFs were a game pretending to be training, and now the pretense is gone. But that argument falls apart when you talk to anyone who actually came up through the scene. The commenter who participated 6 or 7 years ago, who's glad they did it when they did, isn't nostalgic for puzzles. They're describing a crucible. The kind of environment where you bash your head against a binary for hours. Finally understand the vulnerability class at a gut level, and carry that instinct into every system you touch afterward. That process requires friction. It requires failure that feels like failure. And it requires a scoreboard that reflects human effort, because without visible progress, the motivation to endure productive struggle evaporates. The offline competition suggestion from the competitive programming community is practical and probably necessary. In-person events where the work is BF'ly human, but there's something worth grieving in that retreat. The open, online, anyone-can-play format of CTFs was one of security's genuine meritocracies. A teenager in Lagos and a grad student in Zurich could compete on the same scoreboard. Moving to in-person verification means moving to venues, travel budgets, institutional backing. It means the ladder gets shorter and harder to reach. This is the real tension. The tool is extraordinary. The capability is real, and the human developmental pathway it's disrupting was one of the few that actually worked across borders and economic lines. Both of those facts are true simultaneously, and pretending otherwise helps nobody. The question is whether the community builds new structures fast enough to preserve what mattered about the old ones. And while open-source communities figure out new ladders, some organizations have skipped the ladder entirely and jumped straight off the roof. Let me make the strongest case for the other side first. If you have a system that can detect a bug, write a patch, test it, and deploy the fix in 90 seconds flat, why would you optimize for preventing bugs at all? Prevention is expensive. Prevention requires senior engineers arguing in design reviews. Prevention requires saying no to features. Recovery is cheap, automated, and scales horizontally. The math seems obvious. Ship fast, fix fast, move on. Mitchell Hashimoto, co-founder of HashiCorp, someone who built tools that millions of engineers use to manage infrastructure, is saying this logic has a failure mode we've already seen once before, and the question nobody wants to ask is this: what does a system look like from the inside when it's becoming incomprehensible, but all the dashboards are green? That's the question. Not whether AI can fix bugs. It can. Not whether test coverage is real. It is. The question is whether local health metrics can mask global architectural decay. And we know the answer because we lived through it in infrastructure. You could have 5 nines of uptime while your system became a Rube Goldberg machine that nobody understood. Recovery time was phenomenal, right up until the failure mode was novel enough that recovery didn't apply. What I admire about Hashimoto's framing is the precision. He's not saying AI is bad. He's not saying stop using it. He's identifying a specific cognitive pattern. The belief that mean time to recovery eliminates the need for mean time between failure. And noting that we already ran this experiment once at the infrastructure layer, the result wasn't catastrophe. It was brittle complexity that looked healthy until it didn't. One commenter mentions their company raised the AI token quota to $300 per day, and management is pushing engineers to use all of it. That's not a technology problem. That's an incentive structure problem. When the metric is adoption rather than comprehension, you get exactly what you measure. Here's where the open source angle matters. Open systems are legible by design. You can read them, audit them, understand them. The risk Hashimoto described, architecture decaying faster than anyone can track, is amplified in closed systems where the AI-generated code lives behind proprietary walls, and the only people who could notice the rot are the ones being told the dashboards look great. The tool is extraordinary. The velocity is real. And velocity without legibility is how you build systems that surprise you in ways you can't recover from. The interesting engineering challenge isn't making AI write code faster. It's making AI-written systems remain comprehensible to the humans who are still, for now, accountable when they fail. One Vlila human legibility never went out of style. The hardware you can actually touch, modify, and understand. In 1992, Ted Selker at IBM filed the patent on the trackpoint, that little red nub between the G, H, and B keys. It was a genuinely brilliant piece of engineering. Strain gauges measuring force on a tiny stick, translating pressure into cursor movement without ever lifting your fingers from home row. IBM put it in every ThinkPad. Lenovo inherited it, and then, slowly, quietly, they started making it worse. Cheaper sensors, less calibration, drift issues that older models never had. The device that inspired one of the most devoted user bases in computing history got hollowed out by the same company that owned it. This is what happens when a beloved tool lives inside a closed system. The people who care most about it have zero leverage. Ploopy just shipped a standalone trackpoint called the Bean. $35. Open source hardware, open source firmware, running QMK. A 3D printed enclosure with published files. And here's the part that made me actually laugh. It doesn't even use the same mechanism as a real trackpoint. The original IBM design used strain gauges on the PCB. The Bean uses a 3D Hall effect sensor and a spring. It's not a clone. It's a from-scratch reimagining of the concept by people who asked what a trackpoint would look like if you designed it today with accessible manufacturing in mind. Take the original IBM logic to its conclusion. You build the perfect pointing device. You patent it. You own it exclusively for 20 years. And at the end of those 20 years, the device is worse than when you started, because the incentive structure shifted from delighting engineers to cutting component costs. The patent didn't protect the user. It protected the right to make the thing worse without competition. Now take the Ploopy approach to its conclusion. Open hardware, open firmware, modifiable everything. Someone in the comments is already asking for a version you can strap to your hand with push-to-talk integration. Someone else wants just the PCB so they can print their own enclosure with better first-layer adhesion. These aren't complaints, they're forks. Each one makes the ecosystem more useful. The Bean ships fully assembled, but the assembly instructions are published anyway. The firmware is QMK, so the entire mechanical keyboard community's toolchain just works. You don't need permission to make it do something new. $35 a PCB, a magnet, a spring, a 3D printed shell, and the complete freedom to make it yours. That's what happens when the people who love a tool are the same people who control it. Evolution does the same thing with biology. Symbol, push a design until it becomes something extraordinary. Consider the engineering constraint. You have a sensor, the retina, that needs to be the highest resolution, fastest processing visual system in the vertebrate world. Birds track insects mid-flight, spot predators from thermal columns, navigate magnetic fields. This sensor is so computationally dense, it burns 2 to 3 times more energy per gram than brain tissue, and the standard vertebrate solution for powering. Blood vessels threaded through the tissue cast shadows on the sensor itself. We live with those shadows. We literally cannot see the blood vessels in our own eyes because our brains learned to edit them out. Birds said no. This is like an architect designing a concert hall who refuses to put structural columns anywhere the audience can see them. The columns carry the load. They're the proven solution. Every other building uses them. The columns block sight lines. So this architect instead engineers a roof that holds itself up through a completely different structural principle. One that's technically less efficient per square meter of support, but eliminates the obstruction entirely. Christian Damsgaard at Aarhus University spent years measuring gas exchange in bird eyes with microsensors, expecting to find some exotic oxygen delivery mechanism. What he found instead was that the inner retina simply doesn't use oxygen at all. It runs on anaerobic glycolysis, the ancient pre-oxygen metabolic pathway that every cell on Earth used before cyanobacteria flooded the atmosphere 3.5 billion years ago. 2 ATP per glucose molecule instead of 32. 15 times less efficient. And it works. The bird retina took evolution's most powerful energy pathway and deliberately abandoned it to remove an optical obstruction. That's not optimization in the way we usually think about it. That's a system choosing clarity over efficiency. Accepting a massive energy penalty because the architecture demanded it. One commenter nailed it. Evolution doesn't optimize for biochemical efficiency in isolation. It optimizes the whole system. Sometimes the wasteful path is the correct path if it removes a bigger constraint elsewhere. The research has implications for stroke treatment and oxygen deprivation therapies, because here's living proof that highly active neural tissue can sustain itself without oxygen indefinitely, not as an emergency fallback, as the primary design, published in Nature, January 2026. The paper, the data, the methodology, available for anyone to build on. That's how science is supposed to compound. Now, brains that run without oxygen are wild enough, but let's talk about another kind of engineering elegance hiding in plain sight. The number is 255. That's the maximum value an 8-bit colored channel can hold. And in 1996, whether your hardware clamped at that ceiling or wrapped around past it determined whether your explosions looked like fire or like garbage. Dominik Sablivsky dug into something that bugged a generation of players without them ever knowing why. The PlayStation's GPU, when you added 2 color values that exceeded the maximum, just set 255. Done. Clamped. The Nintendo 64's reality display processor, which was technically more flexible, more configurable, closer to what we now recognize as a programmable pipeline. It wrapped around, Your bright explosion plus your bright background equaled a dark, corrupted mess. The RDP didn't clamp because nobody in the hardware design said it needed to. Pull this thread and you find something architectural. Nintendo built a more powerful, more general system. The color combiner was configurable. You could set up arbitrary blend equations. It was, in a real sense, the more open design at the hardware level. More degrees of freedom, more control handed to the developer, and it shipped with a bug that made the most common visual effect in gaming look broken. The fix Zablisky demonstrates is beautiful in that way. Only constraints-based engineering can be. Draw everything at 1/8 brightness into a 32-bit buffer. Now you have headroom, 8 times headroom. Your additive blends can pile up without wrapping. Then convert back down to 16-bit for display. Clamping manually. The color combiner handles the division for free. You just set fog alpha to 32 and let the hardware multiply. The expensive part is the final conversion, which he offloads to the RSP's vector unit, getting it down to about 4 milliseconds. Shipping quality on 25-year-old silicon. What I find genuinely funny is the inversion. The more rigid, less capable PlayStation hardware produced better results out of the box. Because someone at Sony decided clamping was non-negotiable. The more flexible N64 hardware failed at the most basic case because flexibility without defaults is a trap. This is the same lesson we keep relearning in software. Capability without opinionated defaults serves nobody. The PSX GPU was a closed fixed function pipeline that did one thing correctly. The N64's open configurability required 25 years of community engineering to reach the same result. Sometimes the constraint is the feature. The trick is knowing which constraints to bake in and which to leave configurable. And the N-social-TM got that call exactly wrong on blending. The code, the explanation, the fix. All published openly on Fovus Lab. That's how knowledge compounds across decades. One person's curiosity becomes everyone's understanding. We've covered a lot of ground today. Story 10 might be the most ambitious. Pause. EMiX emulating beyond Single-FPGA limits. What happens when your chip design outgrows the biggest FPGA you can buy? This is a real engineering wall. FPGA. Field Programmable Gate Arrays are how you test chip designs before committing billions to silicon fabrication. You load your design onto reconfigurable hardware and run it at something close to real speed. The problem is that modern chips are enormous. A single FPGA can't hold the whole design. And when your prototype doesn't fit on one chip, you're stuck. EMiX is an academic approach to the same problem that commercial tools like Velish have tackled behind closed doors. The core idea: partition your design across multiple FPGAs and manage the communication between them so the whole system behaves as if it's running on one impossibly large chip. The engineering challenge isn't the partitioning itself. It's making the inter-FPGA links fast enough that your emulation doesn't crawl. Every signal that crosses a chip boundary is a potential bottleneck. Run this forward 5 years. Chip designs are growing faster than FPGA capacity. AI accelerators, RISC V-cores with exotic extensions, chiplet architectures, all pushing past what single-device emulation can handle. If the tooling to emulate across multiple FPGAs stays locked inside proprietary platforms, only companies that can afford 7-figure licenses get to validate complex designs before tape-out. That's a bottleneck on innovation itself. The fact that this work is published on ArcSci matters. The commercial emulation space is notoriously closed. Veloce, Palladium, Zebu. These are black boxes with price tags that filter out universities, startups, and independent hardware designers. Academic work that opens up multi-FPGA emulation techniques is infrastructure for the next generation of chip designers who can't write those checks. The algorithms become public knowledge. The techniques become reproducible. That's how the field advances. Not by selling access, but by publishing methods. This has been your daily tech feed for Hacker News for May 16, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voice by Claude Opus 4.6. Voice by Claude Wen 3TTS. Not affiliated with Hacker News or Y Combinator. Now, go build something you can actually understand. We'll see you back here tomorrow.